Finding principal roots is going to be a solving type of direction set that we're going to use, but it specifically talks about an aspect of inverses. So before we kind of talk about our examples that we see here, let's just do a brief review of some inverse concepts. And so one of the key concepts that we want to remember from inverses is the fact that the sine and tangent, or the inverse sine and inverse tangent, are defined from negative pi over 2 to pi over 2. And that gives us the capability of calculating if we have a positive or a negative. But since cosine, which is the x component, would be positive in both of those quadrants, cosine is defined from 0 to pi. So when we're calculating these principal roots, we're going to use this key information to help us just find the one angle that satisfies the equation. Because as we progress down through, what we're going to have is we're going to have equations, and then we have to realize that there's more than just one angle that could satisfy that equation. And actually, there's some scenarios where there might be an infinite amount of angles that would satisfy that equation. So we're going to have to try to label all of the angles, or possibly write an equation or a rule, if you would, that would represent the infinite amount of angles that would satisfy that statement. That's all down the line, though. Today, we're just worried about a principal root, or we're going to find one angle based off of the inverse concept. So let's go ahead and start off here. So if I were to find the principal root of my first problem here, just like I was solving anything else, I identify my variable, and I want to try to get that variable by itself or isolated. So I think we should be able to see that in this problem, we're going to start off by dividing both sides by negative 2, which results in sine of x equals square root of 2 over 2, and we're going to refer to that as negative. Now, this negative is important because that's going to help us identify what quadrant we're working in, but there's also another look for here. And that look for is the fact that any time I see the same value in the radical and outside the radical, we're going to want to rewrite this in its unrationalized form. So I want to actually rewrite this as 1 over square root of 2 with the negative out in front. This will help me identify my side relationships a little bit easier. So that's a good look for us to be paying attention to. Now we'd see that we didn't necessarily totally isolate our x, but our next step would be such that we were going to take the inverse sine of both sides. Oops, not negative sine. Inverse sine, inverse sine. So therefore, we get x equals the inverse sine of negative 1 over square root of 2. Now from here, we're basically just evaluating. So mentally, I like to draw a picture. I see that it's negative, so that's going to tell me I'm down here. I then know my side relationship is going to be negative 1 and square root of 2. So this is going to tell me my 45, 45, 90, or a reference angle of pi over 4. Since I went down, I then know x is equal to negative pi over 4. So you can see that we used that diagram we talked about before. Given that sine or inverse sine was negative, that's what told us we're going to use the values between negative pi over 2 and 0. Now's not a bad time to go ahead and make your own prediction on the second example. And I'm going to go ahead and give you a chance to pause the video before I go ahead and work through the second example. All right, so if we're working through here, I would divide both sides by 2 square root of 3, which would result in cotangent x equals 1 over the square root of 3. Now, another strategy we could use is, we could rewrite this in terms of tangent and then talk about inverses, or we could actually think about the side relationship from here. So just to change gears a little bit, I'm going to actually talk about, how I could solve this now as the statement is written. Because whenever I'm using inverses, I'm basically trying to find an angle. So what this is telling me is it says cotangent of some angle is equal to 1 over the square root of 3. I know that cotangent represents x over y. And again, since it's positive, that's going to tell me that I'm going to actually be in the first quadrant. So now I know my x component is 1. Oops, My x component is 1. My y component is square root of 3. Opposite the square root of 3 would be a pi over 3, or a 60-degree special right triangle. So therefore, I would know my principal root in this case is x is equal to pi over 3. So I could use the inverses, or I could just use my concept of special right triangles. I can use the concept of special right triangles whenever I have a special right triangle relationship. If I have something, that might result in a calculator, then I'd have to rewrite this in terms of tangents to be able to do the inverse tangent of that statement. All right, let's take a look at one more scenario here. And this is one that, at first glance, it might look a little intimidating. Some people see the 3 pi over 2 and they're like, wait a second, what's that doing? All right, but actually, that's all just window dressing. 3 pi over 2 in this case is nothing more than a number. So if I were to go ahead and try to isolate my trig function, I'm going to divide both sides by 3 pi over 2. Well, that's nice because on the left side, I see the 3 pi over 2 is reduced. And on the right side, 0 divided by anything is 0. So I just have a basic statement, secant x equals 0. So now from here, what we end up getting is something that's pretty unique here, though. And let's just talk about it here briefly. And what's happening is we see that secant is actually r over x. So if secant's r over x, I have to think about, all right, when would the fraction r over x be equal to 0? And that's only true if r is equal to 0. But that's where our trouble begins. You see, r represents the radius. And for us to have an angle, well, any angle that's going to be rotating around here has to have some radius. So therefore, basically, we're saying the radius would have to be at the origin, which means it's impossible to draw an angle. That tells us that x in this case is undefined or does not exist. There's no angle such that secant of that angle is equal to 0. But now here's a good question for you. If there's no angle that would result in secant being equal to 0, I wonder what that means the graph of secant of x would look like. Well, that's something we'll talk about more in class or in later presentations.